So today is the first part of our introduction to why we use regressions and what they are. So first, why is this not okay? So first, why economists use regressions. So there's really three main reasons that economists will use regressions. The first is description, to kind of describe the relationship between a few different things, um, and that's honestly like not the most fascinating, but it is the most reliable use of regression. The second option is causation. This is trickier, and there's a lot of kind of special techniques that economists use beyond just regular regressions to kind of tease out the causal relationship between different variables. And then lastly is prediction. Prediction is kind of the sketchiest use, but it is one that economists do make use of. Okay, so this is kind of like if you're going to describe or give a definition of a regression, you would have something like one of the phrases on this slide, right? The sample estimator of the best linear approximation of the conditional expectation of a random variable x given a random variable, random variable y given a random variable x. And to be honest, that's not like the most intelligible. But first, we'll start with some kind of probability basics and build up to understanding what precisely a regression is and does. Just as a side note, this discussion will be about, when we get to the regression portions, we will be focusing to begin with ordinary least squares regressions. And in a later workshop, we'll be discussing some, or at least referencing some fancier methods. And certainly in your cohorts, you're probably going to want to look at some methods beyond just OLS. Okay, so first, probability. So if you have like a universe of potential events, then you can think of kind of the probability of events as a function that assigns a number to an event, and that number has to be between 0 and 1. And we think of it as like kind of, you can think of it in the frequentist perspective, such as like how often you would expect that event to happen. And this is kind of probability using set notation. You have two events, A and B. The probability that A or B occurs is the probability that A occurs plus the probability B occurs minus the probability that they both occur, because that overlap happens twice. You can kind of think of a Venn diagram in picturing this. And then so these kind of are the rules for how probabilities can be assigned. And so there's that rule, and then there's the rule that the empty set or no event is 0, and then the probability is that the entire universe is 1, right? So if you have a whole, if you have a universe of 5 people, the probability of the whole universe, and maybe like each event is like picking a person, right? The probability that all of the people are that like the people picked are from the universe is 1, right? Okay, so and then the last thing is about partitioning, and this is again kind of like think of it in terms of set, but you can also think of it in terms of kind of an image, or you can think of it in terms of like the group of people I mentioned before. So if you have 5 people, and say B is the event that one of the 3 people with whose names come first in the alphabet are chosen, then B1, B2, and B3, the probability that each of those individuals is chosen on their own, must equal the probability that the person chosen is from the group of 3, if that makes sense. So essentially, if you have kind of a subset of events or like kind of smaller events that you can think of that make up a bigger event, the sum of the probabilities of the smaller events must equal the probability of the bigger event. Okay, so conditional probability. This is the probability that something happens given that something else has already happened, or given that you know something else happens. So for example, the probability that tomorrow is sunny given that today was rainy. You don't have this. This is kind of intuitive way of thinking of it, right? The probability that tomorrow is sunny given that today is rainy. But you can also think of it in terms of, if you know tomorrow is rainy, what is the probability that today is rainy, right? So those are, the order in which the events actually occur are not necessarily relevant for kind of the conditioning. And so one thing that's really important So there's kind of two key points here. First is that the probability of A given B is the probability of both A and B occurring divided by the probability that B occurs. And that's essentially kind of a rescaling. It's so if you think of your universe, right, and then you have A and B that overlap, essentially what you're doing when you take the probability of B there is you're kind of shrinking it down to where your universe is now just the space of B, and then you are taking the probability of A within that space. Right, and so then for this partition portion, this is particularly important in the case of B and BC, and there BC is referring to B complement, so B and not B, right? So for instance, if you only have two states of the world, sunny and rainy, the probability that tomorrow is sunny must equal the probability that tomorrow is sunny given that today is sunny times the probability that today is sunny plus the probability that tomorrow is sunny given that today is rainy times the probability that today is rainy. And this is like very helpful kind of computationally. Okay, so independence. Two events are independent if their conditional if the conditional probability is the same as the unconditional probability, or equivalently, if the probability of both events occurring is the same as the product of the individual probabilities. So two examples. I'm flipping coins. I'm flipping a coin, I'm flipping it over and over again. I just flipped heads. What is the probability that the next flip is also heads?
It's still 1 and 2, correct?
Yes. Example 2. A family has 2 children. The first child is a boy. What is the probability that the second child is also a boy?
One over 2.
Yeah, so this is actually a very interesting thing, right? So, and this is the kind of standard answer, right? 1/2, right? And this is an answer. This is a question and an answer that appears in a lot of probability books. But there's something else about example 2 that makes it different.
1/16?
No, sorry. That makes it different from example 1. And it's not that example 2 is necessarily like 1/16 or 1/2 or whatever. The point is that in example 2, we're talking about, we know the information that the family has 2 children. And this is important because when I'm flipping coins in sequence, right, we know that there's a 50-50 probability for each coin, right? When people are having children in sequence, you can say roughly there's a 50-50 probability for each child. But people do not necessarily, the number of children that people have is not necessarily independent of the gender of those children, right? So it's entirely possible that a family, say, has a decision-making rule that they want 2 boys and that they will have up to 4 children, or they'll stop when they have 2 boys. In which case, if you know that that family has 2 children, then the second child must be a boy. Or similarly, a family might want to have a girl and a boy, and they'll say that, okay, well, we'll have X number of kids up until we have a girl and a boy, or we'll have children up until we have a girl and a boy unless we reach X number of kids, right? And so in that case, you would also know for sure in this example, if you know that they have 2 children, that the second child must be a girl. And so something that this gets into that's really important is recognizing that the role of independence is in some cases very subtle. We know in kind of theoretical examples about flipping coins or rolling dice what is and is not independent very blatantly. But when it comes to people's decision-making processes, there's a whole lot of things that can go in, and we don't always know the shorthand independence. The shorthands that we use for independence are not always as reliable. And so it's really key to make sure that we know what kinds of assumptions we're making about people's decision-making rules, right? So if the family has a decision-making rule, we'll just like have 2 children, right? Then like the probability that the second child is also a boy is 50-50. But if that's not their decision-making rule, then we don't necessarily know the probability in the same way, unless we know the decision-making rule. Okay, so now we'll move on to random variables. Okay, so a random variable x can be thought of as, in some sense, a random function that selects from a probability distribution. So for example, and in reality, this is kind of just assigning a letter name to these kinds of distributions of probabilities, right? So you can have like the result from rolling a die, and that's 1 through 6, or or like any of these examples. Random variables do not necessarily need to be numeric, but in general, they will. In general, the ones that we'll be discussing and the ones that economists discuss tend to be, simply because there are a lot of calculations that are very interesting that you cannot do with non-numeric random variables. There are a lot of times when you can turn non-numeric random variables into numeric random variables. For example, in this like result of a coin toss, I could have made h equivalent to 0 and t equivalent to 1, and then it would be numeric. Okay, so probabilities of random variables. So statements about random variables can define events, which is kind of like essentially what we discussed earlier. Events can also define indicator variables, which is super important for a lot of things in econ. And basically an indicator variable is really just like is 1 if whatever it's indicating occurs and 0 if not. Here, these are just kind of a few different ways that people sometimes write indicator variables. And that's not comprehensive. Discrete random variables can be written very familiarly, but for continuous random variables, we need kind of this conception of a probability density. So in this case, for continuous, there should be a less than or equals there. Random variable x has a probability density function f, if this is true, where you can take the integral of f to get the probabilities. And the constraints are that f has to be positive, and that the integral of f has to equal 1. And you'll notice here I've already jumped to kind of ignoring the existence of random variables that like are not numeric. And we then have that the probability that x belongs to like dx, where dx is kind of like a small interval, is f of x dx. So this brings to the question, what does this mean for px equals x? Recall that in our previous slide, we have for a discrete random variable, we can just have px equals x with the probability that x occurs. So, but for a continuous random variable, what does this mean? So basically what this means is that for every individual x, or like little x, the probability that x equals exactly that is 0, which is kind of counterintuitive, right? Like obviously if it's one of the things within the universe must happen, but because of the way that we think about continuity, each individual thing happening is the chance of that is 0 up until it happens, in which case it's been realized, right? So like the probability that like somebody is exactly 6 feet tall is 0, but of course we know that there are people who are, well, okay, maybe we don't know that they're exactly 6 feet tall because of like measurement error or whatever. Okay, so then cumulative distribution functions are sometimes easier to talk about. This is essentially just the probability that x is less than or equal to whatever number. And this is important because a lot of things about cumulative distributions hold for both continuous and discontinuous random variables. And the CDF can always completely determine the probability function distribution. They're also always left continuous, and a continuous distribution will have a continuous CDF. So here's a couple examples. Oh no, that got rotated. Okay. This is, for example, a CDF of an indicator function, right? If you tilt, you can see that like the probability that x is less than 0 is 0, and the probability that x is less than 1 is equivalent to the probability that it's 0, because the function can only be 0 or 1. And then the probability that the function is greater than 1, less than or equal to something that is greater than 1 is 1, because it is either 1 or 0. Okay, these both got rotated. That's really weird. On the other hand, if you have a uniform random variable like so, where everything between 0 and 1 has like an equal probability, you have this function instead, where you can see that it's like a smooth change. over the range that like X can take. Okay, so expectation. So the expectation of random variables is kind of like the average, and on the slide are like some formulas for expectation, and kind of properties. But this is kind of essentially what you're doing is you're taking a weighted average of all the values that X can take by the probability that X occurs. But so there's some interesting questions though about like what expectations are actually telling us, right? So there's a problem that's known as kind of the hat problem, but you can also think of it as, for example, a matching question on a test. N people have given their hats to the coat check, but the identifying information has been lost. If the hats are returned randomly, what is the expected number of correct hats returned? So what's the expected number of correct hats returned if N equals 2?
One.
Precisely. So yeah, so the expectation is 1. But this is actually kind of an interesting example because either both people get their hats back or neither person gets their hat back, right? So even though the expectation is that one person gets their hat back, that's never going to actually occur. And like if you and so it's important to recognize that there are certain cases in which expectations tell us something, but they don't tell us very much. I mean, if you repeated this 1,000 times, then that would tell you that if you had 1,000 pairs of people or whatever, then each pair expectation's 1. So like, you can get that expectation. But that's not necessarily helpful if you really just have the 2 people and the 2 hats. So what expectations do tell us is there's this inequality named after Markov. And basically what this is saying is that you cannot have, like the probability, if you have a positive random variable, that is super large, that occurs has to be small enough that it does not throw off the expectation, basically, right? So mathematically, this is saying that like if you have if like the average amount of cash someone carries is $5, you cannot among a group of like 100 people, you can't have too many of them carrying $1,000 because otherwise you would know that the average must have been higher than $5. Okay, so what is more helpful than the expectation sometimes is the variance, which basically just tells you how much it varies from the mean. So again, here are some formulas. The first, this is kind of the conceptual definition. How much is it varying from the mean? Oh, that is supposed to be an expectation of X. And this is the kind of more computational definition where that's actually easier to compute. The standard deviation is actually the square root of the variance. And with the variance, you get this other inequality called Chebyshev's inequality, which basically tells you that like the probability that you're super far from the mean gets like smaller at rate of 1 over that amount squared. And this is but the thing is that's important is that like, so for distributions that you may have heard of, like the normal distribution, it actually decays a lot faster than this. But the important thing of this is that it holds for any distribution, which can be helpful sometimes. Okay. So then this brings us to the law of large numbers. Basically what you need to know is that if you have a bunch of variables that are independent and identically distributed, meaning that they all have the same distribution, then the average of all those variables, that the difference between the average of all those variables and the actual mean of the distribution, the probability that is large becomes smaller and smaller as n goes to infinity. Okay, so multiple random variables. So you can have multiple random variables and you can describe them in a lot of ways. So there's the joint distribution, which is basically the probability that like something that both X and Y are something. And there's the equations on the screen for what that is in the discrete and continuous case. And then there's the marginal distribution, which is basically analogous to like what we were discussing before, where you just have one random variable and that's its distribution. And the examples kind of show how to compute the marginal distribution from the joint distribution. You can also talk about conditional distributions, right? Again, we were talking earlier about the conditional probabilities of events. Here you have conditional distributions, right? And so computationally, again, this is like the kind of shrinking to the universe where something occurs, and then just like taking the subset where the other thing occurs, except here you're taking kind of the probability that something occurs and then scaling it, right? So it's kind of the same thing. In some ways, you can think of it as a new random variable in terms of like x dependent on y has its own distribution that's different from the distribution of x in most cases. And then you have this like law of total probability, which is kind of analogous to what we had before with the events and the partitioning, which is that, but in this case, if you have the conditional probability and the marginal probability, if you take it over the whole set, you should get the other marginal probability back. Okay, so now we revisit independence. Independence is super important for like everything related to probability and statistics, and therefore econometrics. And so we have several kind of definitions of independence that are all equivalent for random variables. You have that if they belong to these sets, that the probabilities that they belong to the sets are independent. You have that, or that the events that they belong to those sets are independent. You have that you have this as an equivalent, and then you have the kind of definition based on the conditionality, which is that the conditional distribution must be the same as the unconditional distribution for independence. Okay. So there's a couple important properties of independence. And first is that if two random variables are independent, then the expectation of their product must equal the product of their expectations. It's easy to kind of go ahead and assume that that the reverse also holds true, but it actually doesn't. So can you think of an example where it doesn't? Think simple.
Street wet and raining.
Sorry?
Street wet and raining. Such that if it's raining, the street must be wet, but if the street is wet, then it doesn't mean it's raining, kind of thing.
Oh, yes. But sorry, I was thinking of examples of the variables, not necessarily examples of like the statements where like the converse isn't true. But yeah, so this can be a little tricky to think of sometimes, but a good way to go about it is to think about a variable with like expectation 0, where, so for example, maybe you have a set of like 4 points, X and Y, 2 of which are like, and they're on like and 2 of them are on the x-axis if Y is not 0. If Y is not 0, then X must be 0, and if X is not 0, then Y must be 0, and also such that their distributions are such that the mean of them alone is 0 as well. That's kind of a, or not 0. Sorry. And that would be an example. That's a little hard to describe verbally, but yeah. And then the other important thing to know is that if the X and Y are independent, then the variances are also are separable, in the sense that if you have the variance of X and plus Y, you have variance of X plus variance of Y. Okay, moving on. Covariance and correlation. Also something that's important that you've probably heard a lot about, just like vernacular, in like the general vernacular. So covariance can kind of be thought of as like the variance of the two together, in the sense that if you look at this is pretty similar to our formula for variance, right? If we wanted to have the variance of X, then we would just like square this first part and not have this stuff about Y within the expectation. So actually the covariance of X and X is the variance of X. And then the correlation is the same as the covariance, it's just scaled by the standard deviation. And here are some kind of important properties. And this right here is why the variance of X plus Y equals the variance of X plus variance of Y if they're independent, and that's because the covariance is 0 if they're independent, and the sum, and then this goes to 0 and you get this sum. It can be some like good practice in like probability and or statistics to like just practice proving some of the properties, or not not the properties, but like some of the other statements in here. We're not going to go over those because you will eventually in your probability class or your stats class or whatever you end up taking. So I'm just there are going to be points where I'll just like tell you that like a statement is true and you'll just have to like deal with it. Okay. So conditional expectations and conditional variance. So you can also have conditional expectation and conditional variance, or because remember, you can think of the kind of conditional probability distribution as a new random variable. In this case, you then can also have expectation and variance of it. So something that's important to note over here, I mean, this looks like it's just a notational thing, but it's actually very important because here you're picking the number, you're picking the average of, you're essentially picking like the average of X if you have a particular Y. And here you're letting Y vary. So you're really averaging along you're really saying, okay, there is, if you have, you really are talking about the whole set of possible averages for X if you pick a given number for Y. And then the Tower law and law of total variance are like kind of helpful things. Okay, so sampling. So sampling versus the population. You probably hear about this a lot in terms of like sample size for surveys or whatever like that. Essentially what you're doing is you're picking some sort of like buckets. There's some universe of possible rolls. For example, for a die, you can roll a die and that's your sample of this like universe of possible rolls, dice rolls. Or you can pick people versus like the universe of possible people to pick. So the sample is like kind of what gets chosen. You can think of it as a realization of a random variable. You can think of it as the realization of several random variables in some cases. The population, on the other hand, is kind of the overall distribution, the universe of possibilities, all of that fun stuff. So often we have a sample and we actually want to know something about the population. In fact, this is usually the case. Usually we don't know in real life the actual distributions of things, and we have some sort of like realization of that, whatever, and we want to know something about everything else, right? And therefore we use estimators. So, and here IID is independent identically distributed sample, and what this basically means is that each of these is representing a single sample kind of drawn from the same distribution. And so the sample mean is the average of all of those, which is really intuitive. The sample variance is actually not 1 over what you'd think it'd be. It's 1 over n minus 1, and we're not going to get into that, why that is precisely. You can do some computations to see why that is, but it has to do with like the bias, which we'll get into later. But basically, these two kind of very important estimators. And the sample mean in particular is extremely important for us. You may recall that I mentioned that that the regressions have to do with sample means, and that's true because ultimately a regression is looking at a conditional expectation function, but in real life you can't compute it, right? So you have some sort of sample that you're using to compute it. So then you're using the sample mean to approximate your what you're actually trying to look for. And then, but we'll get into that more next week. And so kind of, there's a lot of ways to think about estimators and samples. But something that's there's two kind of things that are very helpful for us. First is bias. The bias is pretty intuitive, right? So by the way, you can estimate other things besides the mean or a variance of a population. There's a lot of different tools that you can use to create estimators and methods to create estimators. We're not going to go into all of those because there's a lot of them, but they exist. You'll learn about them in your stats class. And so basically the bias is pretty intuitive. If you have some sort of estimator that you're computing, the expectation of that estimator minus whatever the actual parameter is the bias of the estimator. And this is basically this is pretty clear, right? Like there's you can have an estimator that is unbiased, and that means that difference is 0. Another measure is the mean squared error. This first equation is the actual definition of the mean squared error. This is based on a theorem about the mean squared error. But basically, the mean squared error is this means it's expected squared error, right? So it's like precisely the average squared error that you would expect from the estimator to its actual thing that it's estimated, to its parameter. And so this is so this can also be written though as like the variance plus the bias, like the variance of the estimator plus the bias of the estimator. And this is why people often talk about kind of a bias variance trade-off. So kind of in an extreme example, right? You could say that your estimator is 0 always, right? And in that case, the variance of your estimator is 0, but the bias is probably super high, unless you're like extraordinarily lucky. And so it's not exactly the case that the two perfectly trade off or anything, but it is true that there is some kind of conception of a trade-off between the bias and variance of estimators. Importantly for us, and for economists everywhere, the sample mean and sample variance are unbiased, which again can be very helpful and is nice to know. And what that means is when we're thinking about computing different kinds of estimators, there are estimators that get, there are ways to compute estimators that get closer to what you're looking for that are perhaps biased, right? Or and so there's some other concepts that are helpful in evaluating estimators that we're not going to go over today, or I don't know if we're going to go over them at all, but they're consistency and efficiency. If you want, you can Google them. So efficiency is based on the idea of Fisher information, which has to do with how much information is going into and being conveyed through your estimator. And consistency has to do with kind of like at the limit, is your estimator getting closer and closer to the real value? And you should, and you should know that note that kind of consistency. You can have estimators in particular that are like consistent but biased, and you can have estimators that are biased but not consistent. And so that's kind of like important to keep in mind, right? That these different measures of how good your estimator is do not all kind of coincide typically. Okay. So now, just like any questions? Oh, if you want, I guess I can stop the recording. I guess really quickly before I stop the recording, this is how to get to this week's exercises. You have to pull from the forks. This information is also in the workshop 1 accompanying materials under like one of the headers. So now I'm going to stop the recording, and if anyone has any questions,